I'm very happy to be allowed to speak on such a topic at an astrobiology training school. So when I was a first-year PhD student, at the end I attended an European astrobiology conference, and I gave a talk with a very similar topic. And I was also talking about modeling plate tectonics, on how it influences surface habitability. And at the end, a very famous German astrobiologist came to me and said, yeah, that was a very nice talk, but where's the biology in it? So I'm very happy that now the definition of astrobiology became much broader, and because for me I think this is also a very important topic, not just to look at the evolution of life and the origin of life, but what it actually has the planet to do with it. Can we say something about how the interior, how the surface, how the chemistry, how the physics actually influences the origin of life and the conditions that you need to have to be able to have life on a planet? And I will start with a rather personal motivation why I got interested in this field. So for me, or maybe everyone looking into the sky, we see so many different stars out there, and we wonder, is there somewhere a different Earth? Is there maybe a planet which is similar to Earth, where life evolved, which looks very similar, maybe even better than Earth? And of course, we can zoom into the sky and with telescopes look at the galaxies, and we have learned a lot about also the statistics. We know, for example, now since Kepler exoplanet mission, that most stars, so most, some people say 30%, 50%, 80%, it depends on the statistics that you believe, most of the stars have at least one planet in their orbit. That's a huge number of planets out there. There's really so many different planets, and we will never be able to look at each of them and to try to find out the different characteristics and look at the atmosphere of these different planets. So we really need to find out, like, what are the most interesting ones there. So which one of these thousands, but now we have several thousands of exoplanets already discovered, but we know that there are millions, billions of exoplanets out there. Which ones are the interesting for us if we want to look for a second Earth? And for most of these planets, we can only have a very rough characterization. So if you're really, really lucky, we know the mass of the planet, the radius, some information about the composition, the age of the planet, the surface temperature. And so can we use this information to say something of how similar to Earth some of these planets could possibly be? And so to first look into which of these planets would be the most interesting if it comes to habitability. Well, the first class of exoplanets that maybe comes to our mind is these hot Jupiter-like planets. So this is not to scale. Of course, Jupiter is much, much larger than Earth. But these were the first exoplanets, or most of the first exoplanets discovered were these huge gas giants. I think if we talk about habitability, we do not really have to talk too much about this kind of class. It's very interesting for the formation and to learn more about statistics, but if it comes to habitability, I think these we can immediately cross out. Emmanuel already mentioned this morning that water-rich bodies like icy moons in the solar system, for example, might be also very interesting planets to look at because one of the main prerequisites, water, is available. But, well, again, my motivation is to find a second Earth outside the solar system. So how would we ever detect life on such a body? So also this is maybe just for the detectability of life and of habitability conditions. If we have a thick ice sheet, it may not be the most interesting class of planets. So what we actually end up is these rocky planets. So planets like our Earth, like Venus, like Mars, and try to find out if we can say something, why are they different in the solar system, and what we can say about this, and also in more general terms. So what are the general processes influencing the evolution of these kind of planets? And of course, once we have a better understanding of why Mars, Venus, Earth, so Mercury and the Moon evolved the way that they did in the solar system, we can then extrapolate it and say, well, what if you have different planets? Like, for example, if you take Earth and scale it up to make twice the mass, or maybe 10 times the mass of Earth, would we predict to have plate tectonics, for example, on such a massive super Earth planet? So super here is just because of the bigger mass with respect to Earth. For these super Earths, we don't even know if they have like a lot of water or no water. But just looking at the mass and the radius, we can say that in principle there may be somewhat similar to Earth just from the composition. And so can we say something about the potential habitability of these planets as well? So just that we are on the same page, I want to give my definitions of a rocky planet. You see that for all these different definitions for Earth-like, rocky, terrestrial, there are always different things that people have in mind. So rocky planet for me means it's a planet composed mostly of matter, silicates. It is big enough that it's differentiated into an inner matter core. Like Earth is mostly made, Earth's core is mostly made of iron, where for Earth at least we have an inner solid core and a liquid outer core. So the magnetic dynamo of Earth, for example, is actually created in this liquid outer part, outer shell of the core. Then we have a silicate mantle, which is what I'm mostly concentrating on in my research. And then we have a crust forming at the surface, which may or may not be covered by water, which may or may not have continents. It has some kind of a crust, can be, for example, basaltic crust, like in most of the other bodies in the solar system. And then, of course, we can try to imagine like different ways of how such planets can look like if we would actually be able to see exoplanets. We're not going to be able for now to see these exoplanets, but you will hear more about it on Friday then in a specific talk about that. But what we could imagine, for example, is we have a planet which may more or less looks like early Earth would have looked like. If we didn't have continents yet on Earth, but water condensed already at its surface, most of the surface would be covered by water. So it would be a water world, but still the mass of the planet, the composition, would mostly be defined by the silicates and the matters in the interior. Or we could imagine planets being very, very close to their star, so that they are tidally locked, like the moon is tidally locked around the Earth, so that only one side of the planet always sees the star, and on the other side it may be cold, it may be freezing. On this side it may be way too hot for life to evolve at the surface, but there can still be some region in between which might be habitable as well. Or we can imagine planets like Mars, for example, where we don't have continents, we don't have plate tectonics. We have one shell, one crust at the surface that may be very old, no plate tectonics, but maybe some small regions of water where some life could evolve around it. Or we could have planets completely covered by life, jungle worlds, they are often called. Or planets that are somewhere in between an Earth-like case or a Mars-like case, where you do have plate tectonics, continent forming, but you have almost no oceans. Like on Earth, 2/3 of the surface is water, but what if it's only 10% water? How would the planet look like? How would plate tectonics further evolve on such a planet? Or we can have planets that may be very cold at the poles and only have like a thin region close to the area, equator, where they might be habitable, where liquid water could be possible. Or in the end have a planet that actually looks somewhat similar to Earth, where we have some fraction of the surface being continents, moving around by plate tectonics, having water and having a climate very similar to what we see on Earth. So how could we actually differentiate between these different planets? Just how could we say what influences the evolution of these kind of planets? One first thing that comes to mind is to go back to the solar system and to have a look at what we actually see in the solar system. So here, for example, you can see a nice arrangement of different figures, different plots of where we've landed at the surface of either planets, moons, or even comets and asteroids. And you can see that if for the solid surface bodies, in a way the surface, they don't look that much different. Some of the bodies, like Venus, for example, have a really dense atmosphere. So the atmosphere of Venus is about 100 times as dense as the atmosphere of Earth. Mars has a very thin atmosphere. Titan is a very interesting body with an atmosphere denser than on Earth, but completely different chemistry. But in the end, just looking at the places at the surface, the only planet that's habitable at the surface is Earth. So Earth really stands out. And to try to answer the question why at the surface it looks so different, we can have a look at the interior and what happens in the interior. And so this is a movie that shows the evolution of the mantle for our neighbor planet Mars, which is a planet without plate tectonics. And what you can see is that here it's a core where a lot of energy is stored still from the accretion of the body and from the formation of the core. At the core, the mantle is heated up, and very hot material, not liquid, it's solid, but on a geological timescale it behaves like a fluid. And so this hot material is actually rising slowly over millions of years upwards. And at the surface, the material is then cooling, or close to the surface, below the lithosphere. The material is cooling, and we have, again, sinking of colder, denser, heavier material, again, back into the lower part of the mantle. So these kind of convective motions in the mantle is something that we would expect for, or at least for some time, for all rocky bodies. So looking again at the rocky bodies in the solar system, or in this inner solar system, we can see here the 4 innermost planets: Mercury, Venus, Earth, Mars, and I added Moon as well. They are all to scale in this case. So how do they differ? What do we know about them? Well, we of course know the size of the different bodies, but we also have a very good idea about what the composition of the interior would be based on measurements of the mass. So this is a sketch of, again, the differentiation into an iron core or metal core and a rocky mantle would look like. So this is, again, Earth, this is Venus. Mercury has a huge iron core, whereas the Moon, on the other hand, has a tiny core, and most of the body is actually made up of silicates. So this already has an influence of how the interior is convecting over time, the cooling, and therefore also the question if plate tectonics could actually ever occur on one of these planets. So what we do know for the solar system, inner solar system bodies, is that looking at Mercury, for example, as far as we know, there was never plate tectonics. So the surface, the crust doesn't show any evidence of any subduction of plates, of any plate boundaries forming. So this is what we call a stagnant lit planet. Venus is not that easy to answer. So there are a lot of different suggestions for what Venus must or could have looked like early on. The problem is that the entire surface was resurfaced within the last few hundreds of millions of years. And we do not really understand yet why. So if it was strong volcanic activity, if it was maybe the end of some plate tectonics processes, maybe it was actually that it was so warm at the surface that the convective motion from the mantle could actually reach the surface and therefore bring the crust down with it as well. So we really don't know. We just know that in the past hundreds of million years, Venus actually reflects or seems to be a stagnant lit planet. Well, on Earth, we know that at least since several billions of years, we do have plate tectonics, even though we don't know what the earlier stage of Earth looked like. And for the Moon and Mars, again, we don't see no evidence or no clear evidence for past plate tectonics. Something else that's important if you want to consider or compare Earth to the neighbor planets in the solar system is what Emmanuel already mentioned this morning, the so-called habitable zone. So the distance from the star where a planet under ideal conditions based on atmospheres with gases like we have on Earth, like N2, for example, H2O, CO2, methane, where if the atmosphere behaves in a perfect way, then surface temperatures could be between 0 degrees Celsius, 100 degrees Celsius, and you could have liquid water at the surface. And if you get closer to the star, of course, it gets too hot, and especially if you have water evaporating into the atmosphere. Water vapor is a very strong greenhouse gas, so you end up with a one-way greenhouse effect and just be getting hotter and hotter. Whereas if you go further out, no liquid water at the surface is possible and would just freeze. These kind of distances really depend on the assumptions of what you put into the atmosphere. So you could also talk about, about hydrogen, helium atmospheres, which would be more from the accretion stage, from the beginning of the formation of the planet. But typically, if you are looking for habitability, we're constraining ourselves to life like we have it on Earth, because this is just the easiest that we could detect. And therefore, we are concentrating also on atmospheres that are somehow resembling the components that we would have in Earth's atmosphere. So let's play the detective. What makes Earth actually special? So why is Earth different from the other planets? I mean, we do have a lot of samples, or some samples in the solar system. What can we learn just by comparing the different planets with each other? So what makes Earth special? Well, we do have liquid surface water, so this is really an important factor. So this depends on the orbital distance. We have an active planet. We have active volcanism spread all over the surface. Actually, a lot of it is related to plate tectonics, but even without plate tectonics, there would probably still be so much heat in the interior that we still would have volcanic activity, which means that we have replenishing of nutrients at the surface. So, for example, if you look at what's the best wine regions are in the world, they are typically related to volcanic areas. So this is really an important factor as well for being habitable on geological timescales. And actually for the other planets in the solar system, most of them show no signs or just minimal signs of recent volcanic activity. So there also seems to be special. Plate tectonics is also important because it is related to producing large amounts of continental crust. So crust that is so buoyant that it's actually floating on top of the mantle, and depending on the amount of water, of course, but on Earth it really means that it's exposed, so the land is exposed in the surface, which is not the case for the oceanic crust. Yeah, of course, life is a special feature of Earth, and one can ask also the question how the different things are related and if they influence each other or not. So what is different for Earth, like how can we compare it then to Mars, Venus, for example? Well, the surface temperature definitely plays a role. And so the question is also how much the surface temperature plays a role for the possibility, for example, to have plate tectonics. The planet size is a crucial factor. The bigger the planet is, the longer the geological activity will last, volcanic activity, but also the ability to have plate tectonics on long time scales also depends on the size of the planet. And of course, the composition. Mercury has such a huge iron core that, that the heat flowing out of the core into the surface is so efficient that you actually need almost no convection in the mantle to cool the planet very, very efficiently. So there's no real driving factor for heating up the mantle at the core mantle boundaries that strongly that you have strong convective motion. And if you don't have convection, you definitely don't have plate tectonics. So therefore, the composition, especially the iron fraction, really plays also a major role. Coming back again to the question of the liquid surface water, maybe you've already seen a picture like this. So this shows what dry Earth would look like at present day if you would concentrate all the water in one bubble. So you see really Earth is actually a dry planet. It's a rocky planet that has tiny amounts of water, so tiny that if we measure the entire mass of the ocean, the surface ocean, it's about 0.02% of the mass of Earth. So it's really almost nothing. I should say, though, that this bubble, the actual size, we don't really know, because we know, of course, how much water is at the surface of Earth, but we have, I would say, no real clue how much is in the interior. We have some lower upper bounds. Maybe we have few Earth oceans in the interior, maybe 1, maybe 10, but we are actually not really sure. But when trying to understand the evolution of Earth, typically we can, the influence of water is really tiny. So let's have a look at how Earth or planets like Earth evolve over time. and how they become the habitable place, or how Earth became the habitable place like we know it. What you can see here is, in a way, a clock of the evolution of Earth, which is not really, the time is not really to scale. But we would start down here with the accretion of the planet. So we've heard a lot about the stage yesterday, about the building blocks of Earth, about delivery of volatiles, about these huge impacts that would still have taken place. And at this stage, there's so much energy delivered to the planet due to the accretion that the interior either completely or at least partly would be molten. So it would be in a liquid state. So this is what we call the magma ocean. In this magma ocean phase, this is when iron droplets, because they are heavier than molten silicate, would actually sink down. They are heavier, so they are concentrated in the center, the gravitational center of the planet, and therefore the iron core would form. At this part, the iron would be completely in the liquid state, and only when the planet starts to cool down, then the iron would start to freeze out in the center of the core, because we have very high pressures in the center of the planet. So at some point, the temperature is just not high enough anymore to keep the iron in the molten state, and it would freeze out, and we have a solid inner core. In the mantle, also, depending on how or what the surface temperature, how the surface temperature evolves in this first time of the evolution of the planet. If the surface temperature goes down, the mantle can efficiently cool out, the magma ocean will freeze out, and we will end up with a state which is somewhat similar to present-day Earth, where we have a solid silicate mantle, an iron core, and we start to have volcanic activity, an ocean at the surface, and building up the atmosphere over time. What you can see here, I just added some example gases of what the atmosphere could have looked like. We really don't know what the atmosphere looked like on the left half of the picture. We know that since about 2.5 billion years, we have a very oxidized atmosphere, mainly consisting of N2 and O2. But how was it actually in the beginning? Did we always have an atmosphere like that or not? And this is something where the interior really has a lot to say. So the interior and the chemistry in the interior influences how the atmosphere is evolving over time. And so during the formation of the planet, the gases that we mostly expect in the atmosphere would be hydrogen, helium, for example, from the planetary nebula where the planets evolved in. But during the freezing of the magma ocean, depending again on the chemistry in the magma ocean, we might expect either reduced atmospheres, so for example, having CO or CH4 being degassed into the atmosphere, or maybe then later on becoming more and more oxidized with having CO2, H2O outgassed by volcanic activity. So having a closer look now into this stage, the first stage that actually set the beginning for the later evolution. Because the question if we can have later plate tectonics or not goes back to the first evolution of the planet during the first millions of years. So in these first stages of planet formation, we also heard something about it yesterday. We would assume that before we create protoplanets, we have planetary embryos that are growing due to collisions between building material planetesimals, either undifferentiated or differentiated. So differentiated means here always that a core could already form, so that the body was originally molten in some state, so that the iron can concentrate in the interior. And when the planets grow to bigger and bigger bodies, at some point, if you have collisions, you can maybe create still some kind of a magma pond, but maybe not put so much energy in the interior that the entire mantle would be molten. So it's really, we do not really know that the last stage of Earth formation, like after the moon forming impact, did we have a magma ocean that was going down to the core mantle boundary? So was the entire interior molten at some point? Or maybe did we just have like a thin shell that that was molten and a solid mantle underneath? This is something we really don't know yet. Depending on, the magma ocean depths would actually influence how many volatiles would be degassed into the atmosphere, and therefore also how volatile-rich, water-rich the mantle would have been in the first billions of years of Earth. And this has a strong influence on what's happening into the interior and later on. So when I think about the atmosphere and how the atmosphere evolved on Earth or could evolve on different planets, I typically look at 3 different phases of sources for the atmosphere. So the first one would be, so this is an example for Venus. The first one would be during the accretion of the planet. We might have a primordial atmosphere, again based off hydrogen and helium, still from the solar nebula. But this is actually an atmosphere that probably would have been eroded away very quickly. So it may actually not be a strong contributing factor to the long evolving atmosphere of a rocky planet. The next phase, this is a more interesting phase, is when we already have a planet forming. If we have a magma ocean and the magma ocean freezes out, most of the volatiles that were delivered to Earth were expelled into the atmosphere. And so this is this primary outgassed atmosphere. And then shortly after that, when the magma ocean was frozen and we start to have long-term evolution of the mantle, convection, plate tectonics, volcanic activity, this is then the long-term secondary outgassing of the volatiles. So just to put this a little bit into dimension, for how much is outgassed at which point and where plate tectonics that comes in. Here you can see an example of degassing from a rocky planet. Here's an example from Earth, from a paper from Noack and Stanton from 2011, where you can see the fraction of degassing of volatiles from the initial mantle, starting from the magma ocean stage over time. So we are here today. This is where the planet accretes. At some point, the magma ocean starts to freeze out. And as the silicates freeze out, volatiles like H2O, CO2, for example, they're not incompatible. So they cannot be built up into the silicate matrix. So they're expelled, or mostly expelled, into the melt. So the more and the more the mantle freezes, or the magma ocean freezes out, the more and more volatiles actually degas into the atmosphere. So it's really most of the volatiles are again lost in the beginning at the end of the magma ocean stage. However, then there are still some volatiles left in the interior, and this is what really sets the interesting long-term habitability of a planet. What happens with these volatiles? But you can see that the rate of degassing over long evolution compared to the magma ocean phase is quite a different amount of volatiles. And just say that the question how long this magma ocean actually lasted depends on a lot of different factors, like, for example, on the efficiency of the atmosphere erosion, also on the composition, and so on. So we can then ask the question, going then to the habitable stage, when was the first liquid water on Earth, or where could it have come from? I would say it was coming from the interior. Why? What we can do is we can have a look at what was probably degassed from the interior during this magma ocean stage. The problem is we really don't know anything about Earth's early atmosphere. So we don't know what was the composition. We don't know if we had a CO2-rich atmosphere, if we had a very reduced atmosphere. Something that I've often seen in presentations is a comparison of the atmosphere composition of Venus, Mars, and present-day Earth. So what you can see here is not the total amount of the atmosphere, but just the composition with respect to carbon dioxide in white, nitrogen in light gray, and oxygen. And one can see that Venus and Mars atmosphere today are very similar, whereas Earth, due to the influence of life, became very oxidized. But we do not know if this was also the case for Earth. So Earth may have, in the beginning, looked very similar to Venus and Mars, or maybe are always in some way representing like a nitrogen-dominated atmosphere, for example. So what would actually determine the composition of this primarily outgassed atmosphere? This is, again, the interior that actually sets this stage of the atmosphere. So we can have a look at, depending on how fast, for example, the magma ocean did freeze out, how many gases were expelled, and what the chemistry was in the interior and how it influenced the first degassing from the interior. And there's a study from, again, from Noack and Stanton from 2008, which is typically like the used as a reference paper to see how much volatiles, depending on how much volatiles were delivered to the planet. If you have, for example, a rather dry initial state, so if you assume that the building blocks of Earth were already depleted in volatiles because the planetesimals could have had melting events as well, for example. Or if you would have a rather volatile-rich magma ocean in the beginning, how much volatiles would we expect to be degassed to the surface? And what we can do is we can take it in reference to the mass of an Earth ocean. So looking at a lot of different scenarios, for example, how deep the magma ocean was after the lunar impact, or how volatile the impactor was in the beginning. In this paper, Lena and Stanton then calculated something between like a small fraction of an Earth ocean or maybe up to 10 Earth oceans of water were expelled from the magma ocean. And at this point, actually, almost nothing or maybe small fractions of water would still stay in the mantle. And we can assume that this water was immediately, or after a short time, condensing at the surface, leading to the liquid water at the surface of Earth that we know was there 4.4 billion years ago. But the question is really how much can actually be degassed from the interior. Something that plays a major role and that was not investigated in that study is, again, the chemistry in the interior. So I said earlier that we don't really know the redox state of the atmosphere. So if the earliest atmosphere at Hadean Earth, if it was reduced or if it was oxidized. We also do not know that much about how it looked in the mantle. So what you can see here is taken from a paper from Scalier and Gaillard 2011, looking at the so it's a so-called oxygen fugacity, which tells us about how much free oxygen is in the mantle that is available for chemical reactions. So we can either have up here would be a very oxidized mantle, down here would be a very reduced mantle. And what you can see is like a sketch of how this redox state in the mantle would have changed over time. So when the core formed, for an iron core to form, we need to have a reduced state in the mantle. So this is something that we know for sure. So we know that when Earth formed and when we had still a liquid magma ocean, we had very reducing conditions in the interior. And this is very important to calculate then what would actually have been outgassed into the atmosphere. We also know from zircons, for example, from the first rocks, that at least the uppermost part of Earth seemed to have been quite oxidized really early on, at least at the time when the oceans were already condensed at the surface. So at some time in between, this condition in the interior changed quite dramatically. So why does it matter? Why should we care about how the redox state in the interior changed if we are talking about habitability? Well, what you can see here are 3 example calculations done by Gianluigi Ortensi from the German Aerospace Center in Germany, where he looked at this really reduced state that Earth must have been in the magma ocean stage when the core formed, going to this really oxidized state that we have right now on Earth in the uppermost mantle. And he was looking at, depending on the temperatures in the melt reaching the surface, what gases would actually contribute to the atmosphere. And what you can see here on the left side is when we have very reduced conditions, we would actually never see CO2, for example, go into the atmosphere, just in very tiny amounts. Whereas if we are at more or less present-day conditions, everything that's degassed is H2O, CO2, classical picture, no problem. So it really depends on what the chemical state in the interior is, what is actually being delivered into the atmosphere. And this is where plate tectonics also played a strong role in Earth's evolution, as I'm going to show in some later slides. So just to, again, to put some examples here, Mars and Moon currently are in this intermediate state in between, neither too oxidized, neither too reduced. The atmospheres are rather oxidized because they are present day made mostly up of CO2, but this is also because the redox state of the atmosphere can change due to also erosion processes of the atmosphere. And early Earth would have been somewhere here on the left side, and today it's somewhere here. So what we can actually do is we can go back to these degassing calculations from Atkins-Stanton from 2008 and say, well, what if you assume that the magma ocean stayed reduced during the entire evolution when the magma ocean was freezing out? How much water would we then get out? Because we know that we started under these reduced conditions. And taking exactly the same calculation, exactly the same example, just looking at what if the chemistry was different in the interior, we would actually get to much, much smaller numbers. So just from the, I mean, of course, we don't really know how much water and CO2 was delivered to the planet, but because we know that at this time the interior must have been rather reduced, it's actually not that much water, ideally in the ideal case about 3 Earth oceans that was degassed and then could condense at the surface. But still a lot of hydrogen would have remained in the interior. And if you assume that then what was degassed in the beginning was actually condensing at the surface, we can then calculate how much water, for example, remained in the interior and could influence the long-term evolution in the interior. So let's look at what actually are different factors that make Earth, a planet like Earth, habitable on long timescales, on geological timescales. Because we learned earlier that Mars, at some point at least locally, was habitable. There was liquid water on Mars for some time, but now it's not the case anymore. So what is an important process on Earth that makes it habitable from the interior point of view? And one thing that's probably quite important is that Earth has a potential to create a magnetic dynamo in the interior, and it actually lasted from the beginning of Earth until today. So as far as we know, there was never a time on Earth where we did not have a magnetic dynamo and therefore a magnetic field. So what the magnetic field does is, on the one hand, in the surface, it shields the surface from harmful radiation coming from outside. So for example, on Mars, we don't have a magnetic field right now. So it would actually not be very healthy for us to go to Mars. We would probably immediately end up with cancer and having different other problems. So alone there, the magnetic field is also already really important. It also has been often discussed that to keep an atmosphere from being eroded to space, a magnetic field might actually be helpful. But it's not yet 100% clear, I would say, at which time frame and how exactly this works. Because Venus, for example, does not have a magnetic field and has a very dense atmosphere, 100 times as dense as Earth's atmosphere. And also measuring how much ions are lost from the atmosphere of Venus, Earth, and Mars today, it's more or less the same. But still, for the surface habitability, I think we don't need to argue that the magnetic field is definitely helpful to have. So somehow Earth managed to have a magnetic field over 4.5 billion years, and Mars and Venus, for example, didn't. Then, of course, plate tectonics itself is alone a contributing factor for long-term habitability at the surface. So one effect that actually Francois is going to talk about this afternoon is how plate tectonics can help to stabilize the climate over long time scales. Depending on if the temperature is rising, then more weathering occurs and more volatiles, carbon, for example, can be washed out of the atmosphere and via the carbonate silicate cycle be subducted into the interior, and therefore regulating the atmosphere for if you have too high amounts of carbon in the or CO2 in the atmosphere. Whereas on the other hand, due to subduction of not only carbon or carbonates but also water, if the water is released again in this region here, in this so-called mantle wedge above the subducted plate, melting can occur again, and therefore more of the volatiles are again released to the surface. On Earth, about 90% of all volcanic activity is related to plate tectonics. So this is really a strong contributing factor for regulating the climate on a long time scale. Something else that I wanted to show here is also, this is a picture of how the oxygen level in the atmosphere changed over time, starting 4 billion years ago until today. And I guess you've all heard about the great oxygenation events that happened 2 or 2.5 billion years ago. What I find quite interesting is that when people start talking about what makes an habitable planet, or is plate tectonics needed for a habitable place, they typically talk about that. They typically talk about us, like could we live on a planet? And when life originated on Earth, the conditions were quite different. So for me, I often think about a habitable planet rather like it was for 3.5 billion years ago. Most of the lives that we had at this time might not actually survive under present-day conditions. But definitely something happened here in this phase. So somewhere between 3.5 billion years ago, oxygenic photosynthesis started. But we did not really see a buildup of oxygen in the atmosphere. So there was quite some delay of maybe 500 million years, maybe 1 billion years, depending on how much was actually produced at this time. And so we can really have a look at what happened at this time, because definitely there's a cut in the evolution of Earth. The way how Earth was more than 2.5 billion years ago, and afterwards is two different pictures. So looking now at all the different feedbacks that we have between in the interior and the surface, putting everything back in one picture, how does plate tectonics, or how did plate tectonics influence the evolution of Earth? So what you can see here is different mechanisms or different geodynamic processes that we have. For example, we have here volcanic outgassing from the mantle into the building up the atmosphere. We have here plate tectonics subducting crust and also part of the hydrosphere in a way, so hydrated minerals into the mantle. The mantle cools the core, and if we have plate tectonics, we actually have a much faster cooling of the mantle than if you would have a stagnant lit planet. Why? Because if you bring cold surface lithospheres deep into the mantle, of course this is a very strong mechanism to cool the mantle. So due to plate tectonics, we have a stronger cooling, and next to the volcanic activity, plate tectonics may well be responsible for maintaining the magnetic dynamo until today. Of course, then the magnetic field, or the dynamo, leads to the magnetic field, which then again shields the surface and maybe also helps to shield the atmosphere from erosion to space. And one of the factors that's linking all the different processes together is again plate tectonics. We can compare this and look at a planet without plate tectonics. So let's take Mars, for example. On Mars, this process right here is missing. So we don't have a continuous subduction of the crust into the mantle. We don't have a strong heat flux at the core or at the core mantle boundary. We don't have a magnetic field. We don't have strong continuous outgassing because we don't have plate tectonics anymore. So alone the comparison between Earth and Mars already shows that plate tectonics plays a major role just in these large-scale feedbacks between the interior and the surface. So one question that we can ask then is, when did plate tectonics actually start on Earth? Do you have an idea when did plate tectonics start on Earth? Well, I would say there's definitely consensus in the community. So the data goes back to somewhere like 4.2 billion years, or up to maybe 1 billion years ago. So it's really not clear. We really don't know when exactly plate tectonics started. And one reason is maybe also because we have to define what we actually mean when we talk about plate tectonics. And what may have happened is that maybe at the beginning of the Archean, at local regions, some kind of resurfacing started, but the global feature, global plate tectonics maybe needed 1-2 billion years to evolve in time. So this is a little bit how I see this picture. We can now again look at what we see from the atmosphere, how it evolved over time. And we can see the time at the end of the Archean, at which time I would say that apart from these two studies, most agree that plate tectonics was active and globally working at this time. This is also the time when we have the great oxygenation event. And so we can ask the question if there's a relation there or not, or if it's just coincidence. First, let us have a look again at how plate tectonics, for example, influences the interior mantle, because I said before that plate tectonics helps to efficiently cool the interior and therefore helps to have a high heat flux at the core mantle boundary, and this is what drives the magnetic dynamo and the magnetic field. What you can see here is an average mantle temperature for a study from Breuer and Moore from 2009. And they looked at how the average mantle temperature would evolve over time from the beginning 4.5 billion years until today. If we either have a stagnant lit planet, like Mars, for example, where in the beginning, due to heat sources, radioactive heat sources in the mantle, heats up the interior, and therefore the average temperature would first increase and then decrease over time. Whereas if you would assume that you have efficient plate tectonics right from point zero, very efficient cooling, so you would end up with a quite different temperature profile, and lithospheric delamination, which is in a way some state in between. And this, of course, the temperature in the interior has a strong influence again of how fast convection happens, if you have volcanic activity, and therefore has a strong influence at what you see at the surface over time. And on the other hand, it's not only that plate tectonics influence the mantle, the temperature, but also the temperature or the heat generated in the interior can also influence the question of if you can start plate tectonics or if you can maintain plate tectonics. Plate tectonics is related a lot to the stress that can be generated in the interior if it leads to breaking the surface into plates or not. And this is, for example, one study by Sandu et al. In 2011, looking at an effect to the heating ratio, so in a way looking at how many interior heat sources release energy over time into the mantle, and how high the stresses can be depending on this heating. And you can see that if you have almost no heat in the interior, if you have a cold mantle, then you have a rather stiff interior. You may have some convection, but it's very difficult to actually break the lithosphere into plates. Whereas if you have very, very high temperatures, a really hot interior, everything is convecting so vigorously that you, again, do not generate any stresses to break up the surface or the lithosphere into plates. So there's some kind of a Goldilocks zone in between. And this has often been used also to explain why people think that in the first beginning of Earth, when Earth was just formed and was really hot in the interior, it was not yet able to create stresses high enough to lead to the initiation of breaking the lithosphere into plates and then really going to plate tectonics. And it first needed to cool down to be able to really start initiate plate tectonics, which may have been somewhere during the Archean Earth. So let's have a look now at some of the maybe coincidences or some of the feedbacks between plate tectonics, surface, life also. So this is a paper by Mac Rosing et al. From 2006. And they postulate that because life originated, please don't look too closely at the numbers. If it was 3.8 or 3.5 billion years ago, we can argue about that. But at some point, life did originate on Earth. And life or photosynthesis started as well. So if you have photosynthesis, you oxidize the surface. So for example, leading to ferric iron instead of pure iron, which again has an influence in the interior on the chemistry and on the redox states that I started with in the lecture. Life also leads to enhanced weathering. So this is a point I'm going to come back to in the next slide. But something that they postulate is also that due to photosynthesis, a lot of the energy radiated from the star, from the sun, can actually be used up by life and made available as energy for chemical reactions. So compared to the energy that comes out of the interior due to plate tectonics, something like in the order of 90 milliwatt per square meter, is much less compared to the energy that life can take from the sun to incorporate then also in chemical reactions at the surface. So in this paper, they postulated that because life originated, more granite could actually form, and therefore stabilizing plate tectonics by forming more continental crust. This is one idea of how life may have contributed to stabilizing plate tectonics on Earth. Another paper looking more closely at this weather effect is from Höning et al. From 2014. There they were also comparing plate tectonics and the effect of life and how it actually is impacts the evolution of crustal formation. And what you can see here is a sketch of the subduction zone. And what they postulate is if you have life at the surface, if you have exposed land already, then due to life, if you have an enhanced weathering, an enhanced sediment layer forming in the subduction zone, that the thicker the sediment layer is, the more water and volatiles could actually be transported down into the mantle wedge. And the water would become destable at some point and be released into the mantle wedge again, leading again to melting processes and leading then to more crust formation, more volcanic activity. So that they argue that because of life, we accelerate this process. So we have more sediments, more water coming down, and therefore more continental crust formed due to more reprocessing of or remelting of crust. And also another point is the more volatile which the mantle is, the faster convective motion can occur, and therefore again accelerating this process. So they postulate that because of life, we have more continental crust production that we would expect if life would have been uninhabited since the beginning. So this is another idea of how maybe the fact that life did occur on Earth could have helped to maintain plate tectonics. In general, if you look at the different occurrence of life, of oxygen in the atmosphere, plate tectonics, formation of continental crust, it all seems to happen more or less at the same time, or at least evolve in parallel. And so a lot of people then have asked the question, is it maybe a chicken and egg problem? So do we have life because we have plate tectonics? Do we maybe maintain plate tectonics because of life somehow helps to stabilize plate tectonics? So this is, maybe there is a relation there, but it could also be coincidence. So I actually see it also a little bit like the stork and the baby relationship. I don't know if you heard of this one. So there's a paper that came out in 2000 of someone looking in different areas all over the world, looking at the birth rate, so how many babies were born in different towns of different size, and counting the number of storks that they could see in the same area. And you can see, even though there's some scattering, there's a very clear linear relationship. So storks deliver babies. Or maybe the larger a town is, the more inhabitants it has, the more babies are born. And the larger the town, the more areas are where storks can live. They have trash that they can feed from. So actually, these two are not related to each other. They have nothing to do with each other. They go both back to a different fact, and this is just as the town is growing. So this is what I call the stork and baby relationship. So let's have a look at some other studies that looked at the evolution of the interior and how it may influence the surface habitability. And I let you decide if it's a chicken and an egg problem or if it's a stork and a baby relationship. So one study, for example, tried to explain how plate tectonics can support I would call it the imprint of life. So with imprint of life, I mean, if you look from outside on Earth, what is the factor that makes you decide that there's life at the surface? Well, it's because you see maybe green life, trees on the continents. So this is an imprint of life. Oxygen in the atmosphere would be a different imprint of life or different biosignature, one would say. So did plate tectonics play a role for these kind of what we would say is how we recognize life on Earth? And so this article was looking at relatively old rocks. In this case, here from the Isua greenstone belt, for example, 3.7 billion years old. And these are serpentinite rocks. So he gave me this picture as an example of a serpentinite on Isua, but I'm happy to ask him again if he maybe mentioned or was looking at a different rock on this specific picture. So the idea behind is that before we had really continental crust, phasic crust forming, the composition of the crust, for example, being rich in olivine and magnesium-rich minerals, if they come in contact at the surface with water, with the ocean, they would actually form serpentinites. So in this reaction, strongly reduced gases are released. So this is not volcanic degassing, this is really metamorphic reactions, leading again to degassing for example, H2 or methane, for example. And therefore, even if O2 was already produced early on by photosynthetic life, we might, or the reason why we actually do not see this oxygen-rich atmosphere at this time, may be because we did not have, or the crust that was produced was still mafic in composition and not what we would call like a continental-like crust. So they postulate that due to later on, about 3 billion years ago, or 2.5 billion years ago, the change in crust composition, which would be again related to the initiation of plate tectonics, which changed the composition of the crust that was produced. This may be the reason why we don't see, or why there was such a delay in the imprint of O2 in the atmosphere, which of course then also makes you wonder, what if we never would have had plate tectonics, never would have had continents? Would we at all see a strong O2 signature, or how strong would it be delayed? Another study looking again about how plate tectonics influences this signature of life at the surface is looking at actually where volcanic degassing happened on early Earth compared to today. So if you imagine on Hadean Earth, we did not have any or not much continental crust, maybe some volcanic areas, but mostly everything covered by water. The volcanic activity would then not be taking place at the surface, but under a deep water layer. So the question is, does it play a role if we suddenly have a huge water column on top of the volcano? Would it change the product of degassing or not? And so in this study, they were looking at exactly this problem. Like if you have volcanoes at the surface, or if you have volcanoes covered by a huge amount of water, how would it change the amount of degassing from, again, looking at an oxidized gas, so in this case SO2, or a very reduced gas? And this yellow range, this is what they postulate would have been in early years. The pressures that the volcano would feel or the magma would feel when the degassing would take place. And so in this case, it would be a strongly reduced degassing. So again, if life already started happily doing photosynthesis, producing more and more O2, as long as we didn't have exposed continents, still the atmosphere would see so much reduced gases being produced and pushed into the atmosphere that the strong signature or imprint of life would not be visible. And only when plate tectonics became more efficient and more continental crust was produced and was floating on top of the mantle, so rising above the ocean, this is when the pressures changes and more SO2 was produced, which life could then also use to produce oxygen. A third study was again looking at what plate tectonics actually does to the mantle wedge. So what happens if you subduct hydrated material into the mantle. And they were looking at, again, this redox state. So again, having more reduced conditions down here, oxidized conditions up here, like you would expect at this time to be occurring in the upper mantle of Earth. And you can see here 3 different regions. The blue region is what we have today in the mantle wedge of Earth. And also in general, if you have initiation of subduction, plates bringing hydrated material into the mantle wedge, again, the redox states that we would expect would be up here. And this is where actually nitrogen can be produced. And nitrogen is what Earth needs. So nitrogen is also one of the ingredients that we need to live and to have a habitable place. Whereas if you would look at the Martian conditions or also early Earth upper mantle conditions, you would be in the region where rather ammonia would be produced, and so this would not build up an N2-rich atmosphere. So again, going back to the question of what can be degassed from the mantle depending on if you have an oxidized or a reduced state, again, what's really helping Earth to become habitable at the surface would be again influenced by plate tectonics, by the subduction of hydrated minerals into the upper mantle wedge, leading to more melting and then to an oxidized melt going to the surface. And of course, we can then wonder if what we see in the atmosphere, this change in the redox state from reduced to oxidized, is this something that we actually see in the rocks or not? So this is, for example, a study from Albach and Stagno, looking at what we can find in Achaean rocks and just before the Great Oxygenation event and after the Great Oxygenation event. So here in this plot, this is present day, and we go back into the past in this direction. In this plot, this is present day, we go back into the past in this direction. So to make it easier, let's turn it around. And then we can more easily compare it. And we can also see here that around this time when the redox state in the atmosphere changed, also looking at the, again, this redox state in the mantle that we can see then, or that has been calculated back from the rocks that we find at the surface, we would again see some increasing trend at the time when the Great Oxygenation event happened. There are also other possibilities to explain these kind of results. If we, for example, assume that there was just different amount of melt produced, but still in a way we know that we had a very reduced mantle in the beginning, so this change is definitely something that occurred in the interior and may be reflected directly in the atmosphere. So again, all these different examples that I just showed on the last slide all go in the same tendency, trying to explain how the interior, how the change in the chemistry in the interior actually influenced what happened on the surface and the possibility to have an oxygen-rich atmosphere. And again, as I said, maybe some of the results are coincidence. Maybe there's a strong relation, maybe there's a weak relation. I also leave it up to you to decide this. But there are definitely a lot of different factors that come together. I wanted to add one other slide that I've seen in another presentation once given, which I honestly don't really believe in that it's a direct correlation, but let's have a look at it. What you can see on the left side is the bio-volume evolving over time. So here's present day. So for how large or living organisms could actually become over time. And you definitely see a strongly increasing trend. Then you can take a different assumption, different studies looking at how strongly the amount of continental crust exposed to the surface evolved over time until, again, here today. So one is the amount of present-day continental crust. If it was larger, it means that in the last billions of years, the erosion of continental crust was more efficient than the production of continental crust. Or maybe it was different, that in the beginning we had almost no continental crust for a long time and slowly increasing. So again, we do not really know which of the different trends are the same, but still similar to the bio-volume, we see an increase in continental crust. Again, I personally don't think that there is a direct relation, but this may rather be a stork and baby problem. Why? Because if, based on the slides that I've shown before, plate tectonics and continental crust formation influence the buildup of O2 in the atmosphere, O2 definitely plays a role in how large organisms can become to have an additional energy source. So again, it may be both results of something different happening, which in this case is the amount of oxygen built up in the atmosphere. Something where I see a much stronger relation is the actual biomass, so the amount of life. Because if you look at present day at Earth, where most of the life is concentrated, what we can see is we have, on the continents, of course, we have a strong signature of photosynthetic life. And also in the coastal lines around continents, this is where, at least looking at the abundance of photoautotrophic life, we can see most of the mass concentrated around or on the exposed land. So there one can probably rather say that plate tectonics and therefore the evolution of continental crust did have an influence on the amount of biomass that we have at the surface of Earth. So let's try to put all the different feedbacks between the interior and surface into one plot. So we have here the component, we have the habitability at the surface and life occurring. We have the mechanism plate tectonics and then related melt and crust production. And on the one hand, starting, for example, with plate tectonics influences, for multiple reasons, the surface habitability, allowing, for example, also for an oxidized atmosphere, stabilizing the magnetic field, stabilizing the climate over long time scales, influencing the composition of the melt, the amount of melt, and also the chemistry in it. Of course, then the melt, how much melt, how many continents are formed, influences again the amount of exposed land, again the atmosphere composition, and the buildup of the atmosphere, and also replenishing nutrients at the surface, which is very important for life. But life, on the other hand, also has a feedback back going into much stronger weathering, and therefore maybe stabilizing plate tectonics together with the volcanic effects. So in the last part of the lecture, I wanted to go a little bit more into modeling plate tectonics. So how can we actually produce or look at the formation of crust, either basaltic crust or oceanic crust or continental crust, and then also model the formation of plate tectonics in the computer model, in simulations. So first to look at evolution of melting and crust, what we need to know first is how is material convecting in the interior of the mantle, and what is the temperature profile that we have. So here on the left side you can see an example for the temperature that we would have in Earth, or an Earth-like planet, starting at the surface. Here we have the crust. This up here is like the lithosphere, so the part that is not actively taking or contributing to mantle convection. Then we have an increase of temperature within the mantle. Here at the core mantle boundary we have another increase. And if we now want to model, if you want to understand how much melt is produced, independent now if it's a plate tectonics planet or a stagnant lit planet, we have to compare the temperature in the interior with the so-called solidus melting temperature. The solidus melting temperature is, the mantle is composed of a lot of different minerals. So each mineral would actually melt at a different temperature. So in a way, having this silicate matrix, if you reach the melting temperature where the first component would start to melt, you would actually not melt the entire mantle in this region at once. You would just start to have small melt fractions occurring. And so in a way, we have in the mantle, we have a minimum melting temperature and a maximum melting temperature. And so depending on where we are in between, we can calculate how much melt is produced and then also rising to the surface and building up crust in the surface. And this is also important to calculate, for example, incompatible elements that are produced into the melt that can then be used by geochemists, for example, to compare to the Earth's rock record. And if you look now here, for example, so here we have convective cells. We have magma being produced at some point. And we can then calculate, for example, where exactly this magma would rise to the surface. We have, for example, some of the magmas reaching exactly the surface and leading to volcanic activity, but we also have intrusive volcanism, so building up the crust from the interior. And the composition, it's a rather complicated process, a lot of factors that are actually influencing what the exact composition of the crust would be, and therefore also what the effect would be, for example, on if you have serpentinization happening later on. So how we model it is, in principle, we can cut it down to 3 equations. So there are the big equations, and I know some people don't like equations, so I also put the video again on top for those that don't like to look at equations. So what you can see here is basically 3 conservation equations. So for example, if you put heat into the interior in the mantle, for example, radioactive heat sources, this energy needs to be dissipated. This energy will be transported via mantle convection in the mantle. We have friction in the mantle, which also leads to energy. We have diffusion of heat from one atom to the next atom without actual convection. So all this needs to be taken into account. The mass in the mantle, okay, we have some degassing to the atmosphere maybe, but otherwise the mass of Earth should not change over time, right? It should be more or less the same. And we have a momentum conservation equation, which means when I have a plume pushing in one direction, the next time step, it doesn't just stop. Because you have a driving factor from the history of convection, generating stresses again, generating pressures on the environment. So which is when the plume is rising up, it influences also how later on convection will continue. So this is in principle only 3 equations. You still need a code of several thousands or 10,000 lines of code to be able to compute it, to make these kind of movies and simulations. But in principle, it goes back to the physics behind these 3 equations. Something, if you want to look now at the formation of plate tectonics and therefore need to know what's actually, how the stresses are evolving, we need to take into account how, if I deform a material, what is actually happening to the material. So for example, if I have an elastic material, if I expose a specific stress to the material, it will deform, but if I take the stress away again, it will relax again. At some point, if I add more and more stress, I reach the so-called yield stress. And any deformation that's happening afterwards, so it's some kind of plastic deformation, is not reversible anymore. So this is what we call then plasticity. And at some point, if I have more stress and more deformation happening, I will actually have a fracture, or in plate tectonics, we call it rather brittle failure of the material. So if you look at the lithosphere, if you look at Earth's mantle, we assume that it does behave like a viscoelastoplastic medium. So visco means at higher temperatures it becomes viscous and it can move, it can convect, what you've just seen in the movie, convection movie. Like an elastic material, the lithosphere at the surface is elastic, but it can also behave at high stresses above the yield stress as a plastic medium, and therefore explain why we can actually break the lithosphere into plates. How this looks like is, for example, here you have a cut into the upper mantle, and this is actually at one snapshot of a simulation that was already running for several millions of years. You can see how a stress pattern, red stands for really high stresses, black for really low stresses, is evolving around a subducting plate. And so I can calculate this convective stress and can compare it to the yield stress that I just had in the last picture. And this yield stress depends on a lot of different factors, and one of the factors is water. So if you have a water-rich material, the yield stress that I need to reach to be able to come to brittle failure or plastic deformation then brittle failure is actually smaller. So this is one of the reasons why it's often stated that water can actually help to initiate plate tectonics. It may not be that easy because also the convective stress is influenced by the occurrence of water. So it's maybe not that easy, but in principle, we can say that the yield stress depends on the water content. And then I compare if the convective stress is higher than the yield stress, then plastic failure will start. And this I can model in my code and therefore model how subduction of a plate is continuing over longer time scales. In a more beautiful video, this is how it looks like then over time. And you can model how plates and continents are forming and moving around over time in these kind of 3D simulations. Of course, due to subduction, plate tectonics influences the redistribution of water in Earth's mantle. And the question is still open, I would say, if water also influences plate tectonics or not. I mean, here's a picture that you can see from the plates on Earth and the different plate boundaries and the movements in red arrows. And typically all the subduction zones is where oceanic plates, which are a little bit denser than continental plates, are subducting underneath the buoyant continental plates. So they bring water into the mantle, but I would say it's still not really clear how much water ends up in the mantle over time, but it influences the chemistry in the mantle. And we can make a thought experiment. What if you look at Venus? Venus is a dry planet, or at least compared to Earth, really, really dry. And would we expect plate tectonics depending on also the surface temperature, because Venus is much hotter than Earth. And we have actually different competing effects if you have these really hot and high surface temperature of Venus. If you just try to predict, could there be plate tectonics, yes or not? And one is, where at these temperatures, liquid water in the crust, the surface is not possible. So, which means, again, the yield stress would be higher. But on the other hand, if you have a warm lithosphere, it also means that the material becomes softer because it's a viscoelastoplastic material. So you would start to have some kind of deformation, which is somehow similar how the convection occurs in the interior in the mantle. So again, the question is, what is actually the most important thing? If you have higher surface temperatures than on Earth, like on Venus, would it make plate tectonics easier or more difficult? And we can run these kind of simulations. And this is actually what we get out of it. So what you can see here is an increasing surface temperature from really, really cold temperatures. So background temperature of the universe. And here we have like an increasing yield stress. So this is where it's very easy to break plates, and this is where it's very, very difficult. And you can see that we get some kind of different regimes. We have a regime here. Interestingly, Earth is almost in the middle of it with a surface temperature of about 300 Kelvin, where we would expect plate tectonics to occur. If we go to more Venus-like temperatures, actually we end up in a more stagnant regime. So it's actually so the effect that the material is dry, the convective stresses are not too high. This is really what makes Venus today be more in a stagnant regime. And if we would actually increase the temperatures even further, which may well have been in the past of Venus, we could have a regime which does not really resemble plate tectonics, but where still resurfacing would be possible. So we can see here that the surface temperature really plays a crucial role in the question if plate tectonics would evolve on a rocky planet or not. Interesting, the range where we don't need to worry about the temperature is the one where we would expect liquid water at the surface. So looking at habitable places, we don't need to worry. Something else, and actually the last point I want to make is the question that I'm often asked, so how is it with plate tectonics on super Earth? Or if we have like small bodies, or if we have a really huge rocky body, is it maybe that if I increase the mass, if I try to predict some kind of a probability of likelihood of having plate tectonics, does it like increase with mass and maybe decrease with time, or what are the relations? Or is it maybe different? Is it maybe like there's a maximum ideal mass where plate tectonics can evolve? How is it? Well, I can tell you right now there's no answer yet, but I can show you what has been published in the past. So this is like now a 2D plot of exactly the same question. Here you have the planetary mass. Here we scale it at 1 Earth mass. And here you have some kind of a likelihood of plate tectonics that is calculated by simulations. Let's put here Mars, Earth. Earth has plate tectonics, so it must be somewhat probable to have plate tectonics. Mars is down here, does not have plate tectonics, so probably the probability is lower. And then we can add Venus, where people are still speculating if there maybe ever was plate tectonics. It's a little bit less massive than Earth. So we do see some kind of a linear trend, right? So we could say, well, if you go to even higher masses, probably we're going to end up somewhere up here. Well, there was a study actually predicting exactly this in 2007, a little bit more than 10 years ago, saying that if you increase the planetary mass, it will be more likely to have plate tectonics. In the same year, there was another study saying no, it's the other way around. Mars being the exception maybe, but in principle going to more and more massive planets, more and more heat in the interior, less and less likely to have plate tectonics. Then there was Korinaga saying, no, actually it's not the mass. The mass shouldn't matter too much. It's the water again, the yield stress, the influence of water on the yield stress, that really matters. And more studies, sometimes going a little bit up, sometimes going a little bit down, and so on. So I fixed them here at 1 Earth mass. But the thing is, the problem is that the question if you can have plate tectonics depends on so many different factors. The mass is just one factor. So none of these studies is wrong. They all have a limited range of assumption, and in the range of assumption, they predict a specific picture. But they have different assumptions, for example, on the water content in the mantle, on the heat budget, on the crust development, and so on. And this is why this is actually a multidimensional domain, but if you just cut it out and plot it like this, we don't know. So the thing is, we cannot say super Earth will more likely have plate tectonics or less likely. It's just one out of a lot of parameters that we have to look at. So since my time is over, I will just show you a quick fun movie for the question of Mars is stagnant lit, so there's no life to be seen. Maybe yes. I don't know if some of you know it. It's an advertisement that was in TV in Germany about 20 years ago when the rover landed at the surface of Mars, and NASA and other people are wondering, how does it look
Take it left 20 degrees.
Well, let's look a little bit around. And then saying, well, looks like a little bit like a rocky planet.
Beautiful planet. Kind of boring though.
So for this,
photo quality
I
from paper. Photo Rec 2.
I hope I
Only
could
from
convince
HP.
you that plate tectonics may have played did play a crucial role in the evolution of Earth to become the habitable place that we know it. And there's still a couple of minutes for questions.